to use cosmic rays in the study of geosciences and archaeology. I am Dr. Jacques Marteau. I am the Deputy Director of the lab that you can see here in the logo, which is the Institute of the Physics of the Two Infinities, which is set in Lyon in France. And during our webinar, we will have a few insights and details concerning these quite new techniques of the so-called tomography imaging, which is a good example of interdisciplinary science between a field which is called particle physics, which deals with the physics of elementary particles of nature, and another field which is close to geosciences and which uses method of the geosciences. So what I would like to do during this short introduction is to give you some insights on the world of the particle physics, and then I will go more deeply and more in details in the tomography imaging. So just to give you a few perspectives, both scientific and historical perspective, as we all know from our beloved Sheldon, everything started with a Big Bang. And from the Big Bang, which is a kind, we believe, of a big soup of elementary elements, particles, which were free to move as they wanted. From this really Big Bang soup, then the universe started to expand, and then those elements collapsed in a smaller structure and started to form nuclei, then started to form atoms, molecules, crystals, and then the ordinary matter as we know it now. The question is here, what do we call elementary particles? So you've seen that in 2 seconds, we went from the really Big Bang to the universe that we know actually on the form that it has right now. And the question is, what is an elementary particle? An elementary particle, as you can see here from this simple graph, is a particle to which we don't know at the time being any substructure, in the sense that we have not found that there are other elements constituting this particle. And the other questions that arise now is, considering the universe, how many of those elementary particles do you need to build the full universe? And actually, the answer is a very limited number of elementary particles. And this is exactly the cartoon that you can pick from the web of all the elementary particles that you need to build the total universe that we have and that we know right now. And in total, these are 12 particles. And this is not completely true because we know that antimatter exists. So to these 12 particles, you should add the 12 antiparticles, which are the antimatter partner of our particles. For instance, the positron, which is E+, is the antimatter partner of our well-known electron, which is E-. And now that we have the bricks of these elementary bricks that built the universe, we can ask ourselves, what is the glue that we have to use? And as we know, right now, there are 4 fundamental interactions, which are called strong, weak, electromagnetic, and gravitational. And the way they work is exactly what is in the cartoon with the 2 boats that you can see in the middle of the picture here. This is a simple experiment that you can do right now. You take 2 persons and you ask them to exchange a ball. And what you will see is that by exchanging this ball, just to conserve energy and momentum, you will have the 2 boats getting away from each other. And with this simple exercise, what you have done here is to mimic an repulsive interaction. And this is the same kind of stuff that occurs between 2 E-, 2 electrons, which we know they are all negatively charged and they repulse from each other. Okay, so you have bricks, you have the glues, and so you can assemble the full universe. And with this is exactly what we call the standard model of particle physics. And this standard model of particle physics, you can have a theoretical view of what it means. Here on the left, you have the full equation that we call the Lagrangian of the standard model, and you see how nice this looks and how fun it looks to solve equation out of this Lagrangian. You have in the middle what we call the Mexican hat, which is basically the fundamental way of generating masses within the standard model, which is a mechanism invented by a guy called Higgs with some colleagues of his. And this is a mechanism called spontaneous symmetry breaking. And you can see that with all these ingredients, you can have a recipe to build up a penguin, which is the kind of what we call a Feynman graph that you see on the right here. This is just to give you insight of how the world of elementary particle works on the theoretical point of view. I mean, in the head of Sheldon Cooper from the Big Bang Theory, for instance. Of course, if you want to assess that what is in the head of Sheldon is actually something that works correctly, then you have to build experiment. And here, this is not the same stuff, because you can see that the level and the dimension sizes of those experiments are really huge. And here is a picture and an event display of the so-called CMS experiment at CERN, one of the two experiments that discovered the Higgs boson in 2012. Now, focusing a little bit on what we will deal with, I will present you now the actors of this webinar. First actor is a particle, and this particle belongs to the list of the elementary particles. This particle is the muon. And you can have here all the relevant information concerning this muon. As you can see, it has been discovered in the 30s of the previous century. So it's almost 1 century that we know this particle now. What we know also is, as it is written here in the about section, the muon is a heavier version of the electrons, meaning that it has properties which are really close to the ones of the electrons. For instance, they all belong to the categories of leptons, leptons being particles which are not sensitive to the strong interaction, the interaction which is responsible of the form of the nuclei and of the nucleus and the nucleon. And there is a beautiful sentence here which states that those muons rains down on us, and it is created in collisions of cosmic rays with the Earth's atmosphere. And so this will be presented more in detail in the rest of the webinar, but this is the source of the particle that we are using to perform our myography experiments on this muon imaging. And when it was discovered in 1937, a physicist asked, but who ordered that? Actually, nobody. But what we have to understand and what we have to remind is that these muons belong to the natural radioactivity. And this is something that amounts to about 15% of the natural radioactivity that we are experiencing constantly, permanently. And there is nothing to do about, because this is something that rains down from the top of the atmosphere. And the number that you have all to remember from now on is that those muons at the sea level is coming with a rate of 1 muon per square centimeter, meaning this surface, per minute. Okay, this is what comes at the sea level as far as the muon is concerned. So this is the first actor. This is the muon, and we will present in detail how we use this muon to perform and to make images of different type of stuff. And of course, you have some humans. So here is basically my introduction to the webinar. I will give you in the next 10 minutes very basic information concerning the myography, and then we will go more in detail, step by step, going from the cosmic rays physics by Amélie and Matthias, who are actually PhD students in Lyon and in the University of La Plata in Argentina. Then we will have a second talk on the application of this myography in volcanology and risk assessments by Marina Rosas-Carvajal, who is a researcher in the CNRS here in France, in Paris. Then another talk of an application which has nothing to do with geosciences, but which is applied to civil engineering. And the talk is called Because Boring is Not Boring, and you will see why. And this will be given by Antoine Chevalier, who is a researcher engineer in Lyon. And the last but not least talk will be given by Theodoros Avgitas, and this will concern the application of all what concerns the muons in the reinforce project. So as promised, now very basics to a new world of image. And as I started to say, we are dealing with the myography, which is a word built on the two words. The first one is muon, the name of the particle, and graphy, which is exactly the same root as the one that you can find in the radiography. There are two types of myography, one which is called absorption and one which is called scattering, but it doesn't matter for what we want to say. The thing here is that the particles that we are using, which are muons, they lose energy and they are scattered along their trajectory inside the matter because they interact with the nuclei and the electrons that constitutes the ordinary matter. And this is this property that we will exploit in order to perform these images. And so basically the ingredients that you need is a particle, a flux, a beam of particle. You need a target. This is the object of your study. And then you need a detector, which is able to count and to tell you how many particles do you count in what direction. And before going furthermore in detail, I want to make a comparison with the medical imaging techniques, because this you will often find in the literature. And I have chosen two known examples. The first one is the MRI, and the second one is the CT scan, the computed tomography, which we also call the X-ray scanner. And I want to insist on some key points which are common, let's say, in medical imaging and in myography imaging. The first step is that you need a detector. This detector is here to perform data measurements. In the first case, you will measure the relaxation times of magnetic moments in the magnetic field. In the second example, you will measure the absorption of the X-ray beam crossing the body that you are looking at. And you will produce with these images, which is the last step that you see on the right, okay? And in those images, you can see contrast between different zones, and you are able to see in these images the distribution of matter that is your interest. And the important point, really, and I insist on this, is that in between the measurements and the image that you get, what you need is a reconstruction technique. So what you have to understand is that this myography imaging technique is not direct measurement, is not a direct view of what you see, but this is a reconstructed image. Okay, and then the scales, the colors, and so on and so forth, they are completely artificial. And this is something that is common to medical imaging techniques, those one, and to the myography imaging technique, the one that we are using and that we are presenting now. This is not like looking through a microscopes for which you see directly the target that you're observing. Okay, and in the geoscience world, this is something that is called the inverse problem. The inverse problem is how do I get from a set of data that has been measured with my detector to the observable distribution within my target. Okay, I measure what I want is an image, and I have to work a little bit. I have to reconstruct. I have to invert the problem from the data to the image that I want to do. In myography, this is the same. We do exactly the same. We start with muons, and we go to the image of the probe of the target that we are studying. So I will briefly go inside this processing chain, and all my colleagues will present you in detail the different steps of this chain. The first step of this processing chain is, of course, what are the parents of the muons? The parents of the muons are high energy, very high energy particles that are emitted in the universe from the explosion of supernovae, of stars, of whatever. And this blow matter inside the universe, this matter is accelerated and bumps into our atmosphere, which acts for us as an airbag and which protects life on Earth because it absorbs this tremendous amount of energy and is distribute this energy among showers of particles. And among these showers of particles, which are initiated at the top of the atmosphere, you can recognize some of our elementary particles, for instance, electrons, photons, neutrinos, and on top of this, the one that we're using now, which are the muons. So high energy particle, atmosphere, and then the shower of all the elementary particles going down to the sea level. Now, why do we care so much about the muons? Because they have properties which are close to the ones of the electrons. So this we already said, but they are more massive. They are 200 times more massive than the electrons. And this is the reason why they can cross the matter on a longer distances than the electrons. And they have the property, for the most energetic of them, to cross up to kilometers of ordinary matters, when ordinary matters means the matter that you can find in a mountain or in the ground or whatever. Okay, and so the targets that can be studied with this technique, they range from the dome of a volcano, and here you see some picture of the one of the craters of the Etna, and you see another installation on another volcano, which is called the Soufrière of Guadeloupe in the Lesser Antilles. So the targets can range from domes of volcano to rather smaller size targets of industrial interest or civil engineering interest. And I will show you pictures of this. And the important point, the common point to all these experiments that we can put, that we can drive on all those targets is that we're sensitive to a parameter, which is here in the top equation, which is called the opacity. The opacity is the cumulated density along the trajectory of the elementary particles. Okay, then, oops, sorry. Then the last ingredient of the processing chain, of course, is the detector itself. How you detect elementary particles. This is quite simple, and this is always the same procedure that you are applying. The idea is that you will pick up a very small fraction of the energy of the particle when it crosses your detector. And this energy that you pick up from the elementary particle, you will convert it into a signal that you are able to measure inside your detector. And basically, there are big families of detectors. Either you convert this energy into optical signal. This is what we use here. And then this optical signal is collected within optical fibers and driven to a photodetector. Or you convert this signal into electrical signal, like a discharge, for instance, or you can convert this into a chemical signal. And with these three families, you have all the type of detection for elementary particle, which starts really from the very first principle that I stated before, that you pick up a little bit of energy of your particle. And once you have your signal, this is quite simple, because what you want is to build the trajectory of your muon crossing the detector. And to build the trajectory, you just need points, and you just need to align points into planes, which could be parallel, which could be of different geometry. But this is something that is like the game for the kids, where you have to join the points to draw a picture. And here what we want is to align the points inside our detector. Just perhaps to complete and to finish my talk, I will give you here some pictures of different use cases. In geosciences, we can use myography, and we have used it for problems of volcanology, geology, hydrology, study of the atmosphere physics, which is, of course, the matrix in which the muons are created, and, of course, the cosmic ray physics. We have also a set of use cases in archaeology to study the pyramids, tumulus. You see a picture here of a tumulus, which is a tomb, anthropic structures, ruins, whatever. And of course, there is also a set of application in the industrial controls for what we call the non-invasive and non-destructive controls, because you can do the image, you can do the myography of large structure like blast furnace, or like civil engineering problems, or stuff like this. Other pictures of our installation in the world, on volcanoes, inside underground tunnels, close to a blast furnace, or to a nuclear evaporator. You see, each time we set up a detector, we face the target, we measure the absorption of the incoming muon flux, and then from this, we reconstruct the size and the distribution of matter inside the target. For instance, here, the example of the La Soufrière dome. So you see from the top picture here, the dome, and you see in green all the position where we put detectors all around the dome. The idea being to collect and to interconnect the views of the different detectors in order to perform 3D images, and you will see example in the next talks. And this is the type of image that you can reconstruct by looking at the dome of the La Soufrière from 4 different points of view. And you see the mass distribution. In blue, the zones which are not so dense, and in red, the zone which are more dense. And this is our view of the dome. And this is an insight and an input to volcanologists to perform modeling of the behavior of their beloved volcano. So these are basically the big steps of the myography imaging processing. And now I will give word to Amélie and Matthias, who will present more in detail the models of cosmic muons production and propagation inside the atmosphere. Thanks for your attention. Amélie, when you want.
Yes. Do you see my screen? So someone see
Not
my
yet.
Not yet.
Not
No.
yet.
Okay. It's okay.
Yeah, very good.
Yes. So hello everyone. I'm Amélie Cohu, and Mattias Tramontini and I are PhD students, and we will present you cosmic rays from heaven to underground. So what are cosmic rays? So cosmic rays are high energetic particles that travel through space at nearly the speed of light, and they are composed of 90% of protons, 9% of alpha particles, and only 1% of heavier atomic nuclei. The most energetic cosmic rays are millions of times more energetic than the highest energy particles we can produce in our most advanced particle accelerators, such as LHC at CERN in Geneva.
Sorry, Amelie, we don't see we see the first slide. We are not seeing the.
Yes, and we need to put it in presentation because it seems that they are a little small.
I don't know.
Better. Now it's better.
Yes, that's better.
So you can see the second one?
Yes.
Yes. So sorry. So in this image, you can see particles that will enter in the atmosphere, interact with the particle in them, and reach the ground. So cosmic rays particle hit the Earth's atmosphere at the rate of about 1,000 per square meter per second, and all the time, and from all directions. So since when do we know the existence of cosmic rays? So this took place soon after the discovery of the electrons and the radioactivity. So at that time, the radiation was believed to come from the Earth's crust. And in 1912, physicist Victor S. flew a series of high-altitude balloon flights, so up to 5,300 meters of altitude. He discovered that the radiation of very great penetrating powers enters our atmosphere from above. And he repeated the experiment during a solar eclipse and observed that the sun was not the only source. So, using instruments on board balloons, S and his colleagues showed in 1912 that the radiation that united the atmosphere has cosmic origin. S was Nobel laureate in physics thanks to the discovery of cosmic rays. To continue, where do cosmic rays come from? This is not yet fully known, but scientists think that nearly all of them
We're
come.
still frozen on the third slide.
I don't know why.
That's okay,
I
correct.
believe you will have to change it with the mouse.
Yes, you have to change manually, I think.
With my mouse, it's
Yeah.
what I did. So
Okay.
maybe I can stay in this. So here you have the S balloon.
That's the balloon experiment.
Sorry. So this is not yet fully known, but scientists think that nearly all of them come from outside the solar system, but from within our Milky Way galaxy, and this would concern particles of smaller energy. And the very highest energy cosmic ray with an energy 1,000 times greater than those of our solar system may have extragalactic origin, and they are due to black holes or gamma bursts, for example.
Okay, let me share my screen.
Okay, now we'll hear Matthias from Argentina.
Okay, hello everybody. So what happens when comet rays reach the Earth? Well, once they reach the Earth, they interact with the atmosphere and produce extensive air showers, which are cascades of subatomic particles and electromagnetic radiation. In this slide, you can see a simulation of an extensive air shower that was initiated by a proton at around 20 kilometers of altitude. Note how a single proton, in this case, produces hundreds of other particles, among which we find protons, neutrons, electrons, and muons. In this animation, the trajectories of different types of particles are represented with different colors. Note all particles that are produced in the shower reach the ground. Among the particles that do so, muons are the most abundant ones. About 100 muons per square meter per second reach the Earth's surface. That is about 1 muon per minute through the tip of your finger. So how do we use cosmic rays to study geological bodies? In this illustration, you see air showers over the Guadalupe Island in the Caribbean Sea. Here are illustrated just a few of them, but as Amelie said, they are produced constantly and arrive at the surface from every direction all the time. So to study geological body, we use, from all the particles that are produced in the showers, we use the most energetic and abundant ones, that are the muons. So let's take, for example, the Sospero Guadalupe volcano, which you see in this image. The principle of the method is that the higher the amount of opacity along the trajectory of the muons inside the target, the lower will be the muon flux crossing through it. So, in order to study a geological body, we deploy a muon telescope pointed at the target that registers the number of muons that traverse the geological body over a given period of time. You can see a picture of a muon telescope deployed on the field on the left of this image. Given that the detection panels of the telescope are divided into pixels, we are able to reconstruct the trajectory of the detected muons. This trajectory defines what we call the axis of observation of the telescope, which are represented in this image with yellow straight line. With this data, we calculate the flux of muons that crosses the volcano along each one of these directions. And finally, through numerical modeling, we convert the muon flux traversing the volcano into average density along its trajectory. Here you see a muon radiography as seen from the telescope position on the left of this image. Each pixel in this image represents the average density along a given axis of observation. To conclude, muography allows us to study how the mass is distributed inside a geological body, and with this method we can detect density contrasts inside targets such as denser regions, weakened zones, and voids, which you will see more in detail throughout the following presentations. Thank you very much for your attention.
Thank you, Amelie and Matthias, for the presentation here on the muon flux, which is one of the key inputs, as you understood, of the muography imaging, because this is actually the probe which is going inside the matter and which is absorbed or scattered, and this will be used after this to reconstruct the image. So don't forget, if you have questions and answer, yes. So there's a question here: for how long do you keep the receptors to manage to have the image of the volcano density? So this is a good question that arise quite often. The question is, how long do you have to stay? The main difference with the medical imaging techniques that were shown before is that here we don't have any control on the source of the particles. The incoming beam is given by the nature, and there is no way of increasing the intensity or changing the energy of the particles. If you want to do this, then you have to build a small CERN, a small accelerator complex, in order to generate your own muons, and then to shoot your target with the beam, which is actually something that is absolutely infeasible. And so the limitation of this technique, of course, is given by the amount of flux that Mother Nature is sending on your target. And here, typically, to have the image of this dome, which is, let's say, half a kilometer size in all directions. This is a typical size of this volcano. You have to leave the receptor from 1 to 2 months in order to have your first 3D image produced in the with this type of detector. Yes, of course, the incoming beam is a function of the altitude, the zenith angle, latitude. It is sensitive to atmospheric condition. This is sensitive to magnetic field at the Earth. This is sensitive to all the environmental parameters that you can think about. What I propose now is that we move to the next talk, which will be given by Marina, and then we will continue to answer to the questions in the Q&R. And so either I type directly the answer on the Windows, or I answer it orally. So please, Marina, with the interdisciplinarity at work on the volcanology and risk assessments.
Okay, thank you. Hello, everybody. So my name is Marina. Thanks for being here. I'm a volcanologist. So what I will talk about during the next 10 minutes is how we use this pretty novel technique of muon tomography to better understand what happens in volcanoes. Can you guys see my slides? Jacques?
Yes,
Yeah.
yes, perfectly.
Cool. So before going to muons, let's take a step back and see the broad picture in volcanology. So what are the current challenges that we are facing as volcanologists, and just to see then how muon tomography can help us to better understand volcanoes. So probably all of you know that most of volcanic eruptions happen because some kind of magma is ascending from what we call a magmatic chamber that is located deep to the surface of the Earth. Now, this magma comes up and this provokes huge eruptions. But actually, there are other types of volcanic eruptions that do not necessarily involve the ascent of this magma to the surface. For example, this is what happened in Mount Ontake in 2014. And so these kind of eruptions are currently the most unpredictable type of eruptions, because traditional methods to study these eruptions involve methods that actually track the magma going up. So the problem here can actually see what's happening when magma is not involved. So how do these eruptions occur? Where what we think so far happens is that actually there is in the shallowest part of volcanoes, which we call hydrothermal systems, there is a lot of water, liquid, basically meteoric water, so rainfall that infiltrates in the volcano. And this water gets progressively heated up because of the magmatic gases that ascend. So this is not magma, but it's just gas, hot gas, and liquid also that rises up towards the surface. Now, as this water gets progressively heating up, temperature increases, pressure increases. And so you can think of a pressure cooker. And the idea is that at some point, this pressure is too high and the eruption occurs. And so what we're trying to see here is basically what are the processes that lead to this type of unpredictable eruptions. So some of the big questions that we face in this field are then, as I said, what happens normally, meaning typically in the shallow part of volcanoes, so the volcano hydrothermal system. And by normally, I mean when there is not an eruption, what are the normal processes that happen inside? And what are the links between the things that we can actually measure at the surface of a volcano, for example, temperature, fumarole flux, the geochemical composition of a fumarole, and so on. What is the link between what we observe in the surface and what happens inside? So that we can say if there is an abnormal behavior, what is happening inside. So how do we try to solve these questions? Well, we use an integrative approach where we are combining, of course, observations, and we need as many observations as we can to understand the full picture of the processes inside volcanoes. we want to characterize these processes so that we can feed what we call numerical models. So these are computer models that can reproduce the physical and chemical processes that happen inside a volcano. Now, if we can constrain our numerical models with new observation, then we have what we call calibrated models of the volcano functioning. And so we can use these models to predict what will happen if abnormal activity takes place. So here I will focus obviously on the observation part, because muon tomography is a new tool that we use as volcanologists to know how the volcano interior is and what are the processes that happen inside. So the idea is the following. We will use, as I said, muons to figure out what goes on inside volcanoes. In the picture on the right, top right, you can see, let's say, a summary of what you already heard by Jack and Matthias. So we use the normal normal flux of muons that comes at the surface of the Earth. And these muons that arrive, they will go through the volcano, they will interact with the volcano, and they will lose energy as they go through the volcano. And the way they lose energy is according to the volcano density. So if we put a muon detector on the right side, or on the other side of the volcano, and we compare the amount of muons that we measure after going through the volcano and then with the amount of muons that normally arrives to the surface of the Earth, we can have an idea of what we call the opacity of the volcano, or the density, basically the average density along the path of the muon. So we go to our volcano. I will talk about La Soufrière de Guadeloupe. We put our muon detectors, and also, as you heard before, the idea is that each muon detector can scan many different axes of view, let's say, of the volcano. So we have different directions, and at each of these, we can actually determine the average density of the volcano to build a muon radiography. So the first work that I want to talk about is this muon tomography, three-dimensional muon tomography that we did on La Soufrière. So the idea here is exactly as Jacques described it in the beginning. If we have one single detector, what we can do is muon radiographies, which are two-dimensional, and this would be equivalent to you getting an X-ray radiography of your body. So here you can see in the center image, there are 3 muon detectors that were located at different points of the volcano, and these are scanning the same volcano from different points of view. And for each of these, we can build a muon radiography of the volcano. Those are the figures you see on the right. But now you can also see that these 3 detectors are scanning the same region of the volcano as well. So what I work on is mathematical techniques, basically, that help us reconstruct what is the 3-dimensional distribution of this density of the structure of the volcano inside from these different observations. So this would be analogous to the CT scan, as Jacques said. So no, we don't have the radiography, but we have the full 3D tomography. So on the left, you see this model reconstructed of the density distribution of the volcano from the different muon observations. And in blue, you have the low density anomalies. So these are the regions where the volcanic rock is mechanically weak. And why is this weak? This is because of the alteration that the rock has suffered from the huge circulation of magmatic fluids and hydrothermal fluids, as I told you in the beginning. So these fluids are very acid, and they basically eat up the rock. They alterate the rock, and so this makes the density go down. And then in red yellow, you have places where the rock is very dense. This means fresh lava deposits that have not been altered by this hydrothermal alteration. On the right, you see a slice of the same model on the left. So this is a horizontal slice, a horizontal cut of the model, and you can see that there is this very dark blue region located at the let's say bottom part of the model, and this is very interesting because what we see is that the most altered rock is located right below the places where we see most of the activity of the volcano. So all the red stars that you see in this figure are locating the fumaroles, the active fumaroles we have, and the square is actually a boiling acid lake. So this confirms actually that this hydrothermal fluid circulation is actually altering and making our rock weaker and weaker. So we use these structural models. We combine them with geological data, with geochemical data, GPS data, and so on. And we come up with conceptual models of how the volcano works. In this case, this is an interpreted section of La Soufrière, where the pink region that you see is what we think it's the main hydrothermal reservoir. So that's where most of the magmatic fluids are arriving to the surface of the Earth, to the volcano. And this is where the most weak rock is located. So what we did in this work is that we think that because of this high fluid circulation, the rock is getting more and more altered. And so there is a part of the La Soufrière volcano that it may collapse just because of its own weight over a very, very weak material. The other thing that I want to point out that where muons can help us a lot, it's on actually monitoring. So far I talked about structures, but the idea is here that if you leave your detector as much as you can on your volcano, well, you can continuously track the arrival of muons. And if there is a change inside your volcano, a change in density, then you should see a change in the amount of muons that you receive. So this is what we did. And we actually were able to detect some regions of the volcano that experience some sort of density change. Because basically, as you see in the lower figure, the amount of muons that we receive changes over time. So you can see in the red line that at certain point it goes up. This means that we're receiving more muons. So this means that actually the density of the volcano has decreased. Now, the question would be why it has decreased, what is the density change that we can observe at this level of the volcano? So this is very shallow compared to magmatic chambers and so on. Well, what we think is actually that some sort of reservoir has been emptied. And so if you remove the water from the reservoir, then your density goes down. And this is what we were able to detect. What we're currently working on is in combining different detectors at the same time to see if we can better locate where these changes are happening. So if we do this, we will have a method that can allow us to track the dynamics of the volcano in almost real time and see what are the typical movements of fluids so that we can then compare it to what will be abnormal activities. And with this, I thank you for your attention.
Thank you very much, Marina. This was perfect. So you've seen the tour on some volcanoes. And so although the talk here was focused on the Soufrière of Guadeloupe volcano, this is a technique that is used on volcanoes in Italy, in Japan, in Asia, in many parts of the world, because there are many volcanoes in the world. And this is actually something, a technique which is in full development because of this structural imaging capacity and also because of this monitoring capability that Marina pointed out.
I see two questions that relate to the same thing. If you want, we can go ahead. So the two questions are about combining muon tomography with other methods, for example, gravity, which is very smart because gravimetric methods, they are sensitive to the same physical parameter as muons, which is density. And so the question is, can we combine them, or how do they compare? And actually in the very first work that I show you, I didn't mention this because of time, but we are actually inverting together gravimetric data and muon tomography data to have a better constraint, a better resolution. And then in terms of the details, where it's complementary, I would say, because gravimetry is sensitive not only to the lava dome, but also to what happens below. And so sometimes you would say if your gravimetric network is not very high resolution, you will have as good resolution as you have with the muons. But then the muon helps you constrain better the surface part, and then with the gravimetry data you can go deeper. So it's highly complementary. That's it.
Okay, very good. Thanks for the answer. I also answered to another questions concerning the online processing. So this we can insist a little bit on this. Of course, you need to accumulate statistics with those muons. I insist once more, there are two limitations actually. The first one is of statistical origin, because you cannot act on the source, you cannot increase the intensity of your flux. So if you have a large target, of course, it will absorb a lot of muons. And so since your detector is after the target, you have to wait enough time in order to have a statistical signal, a signal which is statistically relevant. And the other limitation is that, of course, I didn't insist on the intro, but this should be obvious from now on. You can see only above the horizon, okay, because the particles, they are produced on the top of the atmosphere, and they are raining down to the ground level. So you cannot use this technique to look below your horizon. That's these are the two main limitations. So if you want to scan or to make an image of underground, then you have to go deeper still and to look above your head. And this was my transition to the next talk, which will deal with boring techniques, which are not boring actually, but which refer to tunnel boring machines, which are the big machines that are used to drill the tunnels of the subways all around the world. And we have made an interesting application of the myography to this particular types of problem. And then I leave now the door open to Antoine, who is an expert in this type of applications for tunnel boring machine. Antoine, please.
Okay, first check. Is it working?
Yes, actually this is.
Okay, can you see the first slide when I'm moving it? Okay, great.
Moving.
Okay, hi everyone. I'm very happy that we are all here discussing about this. So I'm Antoine Chevalier and I'm working as a research engineer in the team on civil engineering applications, industrial application, etc. and so on. So we wanted to develop those aspects of myography, and we are to provide some services to the private companies around us. So now I'm going to talk about the subject I'm spending most of my time on. And this is the tunnel boring machine. Most of them now in France, in Paris, there is a huge project ongoing that is to build 200 kilometers of subways around Paris, which is the double amount of what already exists and what is probably already pretty well developed. But it's doubling the size of the subways around Paris to make it bigger and easy to improve the access of the suburbs around Paris. So mostly 4 new lines and extensions of 4 already existing lines. During this project, there will be probably at some point 21 tunnel boring machines, which are those big wide machines that range from 10 to 17 meters wide shields. This is the front part, which are drilling tunnels and building them at the same time, which means putting some huge concrete arch every 2 meters and building them while boring holes. So we were involved in this project as the myography team. They wanted us to provide them a daily reporting, which means a daily 3-dimensional radiography of what they might encounter during the drilling. And they wanted us to provide them an alert level, depending on what they were going to cross. Like they wanted to see if there was going if they will encounter a weakening or strengthening of the rock in front of them. And this was a challenge because at this time we were only doing very static radiography, the kind of one you saw before, 3D ones sometimes, but never with moving detectors, because the detector will be mounted on the tunnel boring machine, and they would move, and they will move. So that's what our challenge, and it gives us the opportunity to improve our algorithm and question our own methodology. So basically, a tunnel boring machine in reality is just like this, a big cylindrical machine where we would put some detectors. You can see them in the middle and in the right. We have put sometimes two detectors, up to two detectors on the machine, one close to the shield, which is drilling and protecting, which is drilling in the ground and protecting the people in the machine from rocks falling. So at first, because we always need to to reinforce the confidence of the industrial people on new technology, they wanted us to prove that we were able to see them drilling the hole live with the radiography. So we have put a detector on the side, and we were looking at the advance of the tunnel boring machine for 100 meters. So what you see now is our two radiography. First one at the beginning before the drilling on the left, and a radiography 16 days later, showing the advance front by a weakening of the apparent density we saw. You have on the right the representation of what we were looking at, and we see good results in the weakening. So now that we have gained the industrial trust, we had mounted a detectors on the tunnel boring machine, and we had to develop algorithm to reconstruct what we have, to reconstruct a dynamic into many two-dimensional myographies taken at different time while the tunnel boring machine is advancing, and then combine those two 2D myographies into a 3D reconstruction. Here it's a simulation. You can see on the left a basic representation of what the tunnel boring machine is. You can see in the middle two myographies showing the different myographies we are expecting from these simulated models at 3 different points. And you see this density anomaly growing on the image we saw and then disappearing because the tunnel boring machine don't see it anymore. So with those images, this sequence of image, we can try to reconstruct the anomaly. Here you can see this cube is reconstructed slightly diffused because we don't have the resolution in the depth to properly put this anomaly in 3D. But still, it's still interesting to do this kind of measurement. So we continued. What we really need to do this is a proper digital innovation model, because we need to know exactly what is the amount of rock we are seeing in any given direction. We also need an exact positioning of the detector, especially its orientation, its inclination, because it has a huge importance in the differential flux we are basing our reconstruction on. And sometimes we need the building footprint map, which is something we never have because it's not very well documented, and we hope in the future it will be. So this is the kind of reconstruction we provide to tunnel boring pilots actually. So you can see the shield represented in the gray, and we interpret the whole image 40 meters in front of the detectors. As you go, as you increase the distance between the shield and the detector, we don't see, it's almost pure prediction, and we have a decreasing resolution as the distance increase from the shield. You can see here is the longitudinal slice from this TBM, and three in the lower part of the screen. You can see 3 slices of that cube, showing some weakening anomaly in blue and strengthening anomaly in orange. We have validated some of these images on known targets. There was some well already made during the drilling of the new tunnels. This one was a big structure, so we really wanted to see it. We were not knowing of it. We were not knowledgeable of its existence before it was rendered, so we were pretty happy to discover that we had discovered afterwards. So you can see this big well that is rendered as a weakening of density, well located on top of the tunnel boring machine, but not so well located beneath, because this is where we have the less resolution, because this is where we have no muon anymore. And we have uncertainty to where to position the density weakening due to the fact that we don't have a sufficient resolution with the angle we are looking at. We also found a pretty massive density weakening when we were arriving to the pre-holes that are made to where the tunnel boring machine finishes their course in the future stations. These consist of big rectangular holes of 40 meter deep. And you can see this kind of big, massive lack of density that are shown in our detectors. This is the kind of, on the right, you can see in blue, the kind of anomaly we raise when we find a continuous weakening with a consequent volume of more than 20 or 30 cubic meter. This one is pretty big, actually. We throw an anomaly detection error and say, you are encountering an anomaly. Please take that into account. So I'm feeling it's still, the first results are very promising, but everything is still very ongoing. It's very new. We were developing every algorithm I showed you almost live, and we were already late during the development because industry is always wanting more. So we hope it has a bright future inside. Thank you for your attention.
Thank you, Antoine, for this nice presentation of quite original application of muography. And just to make a clear parallel and comparison of the job that Antoine has done, it is equivalent to take a picture when you are in a car and that the car is moving, and you have to reconstruct with the images that you take in a time lapse, for instance. You have to reconstruct all the landscape that you are taking in the picture. So this is quite a tough job, and actually this is a quite nice application of the muography. So meanwhile, we answered some questions online. So since there are no open questions right now, I propose to move to our last speaker for this afternoon, who is Theodoros, and he will present what has been made available now on the Reinforce website and within the Reinforce projects. Please, Theodoros.
Yes, thank you. I will go through how we plan to make a citizen science project out of muon tomography. So I will first start by saying that since ancient times we know that people strive for the acquisition of new knowledge or the re-evaluation of the knowledge that we have. So today amongst these people, there are those that want to do scientific work, mainly during their free time. And sometimes these people don't even have formal scientific training. We know that because of all the social media and the new communication tools that we have, sometimes these efforts are a bit diluted because they are communicated in a personal YouTube channel or a small Facebook group. So our intention here is to provide these people with a global communication channel where they can unfold all their talents and work in a scientific environment that is that should be promoting solidarity and openness for its members. So this is what we are aspiring to do. Zooniverse is the kind of platform that helps professional and amateur scientists come together in order to work on their fields of interest. And we are lucky because, as you saw through all these presentations, muon tomography stands on the crossroad of various scientific disciplines. And we believe that in a similar manner, we can bring together citizen scientists that have diverse interests. Moreover, through this collaboration with citizen scientists, we can have them experience and access to our laboratories and the equipment and the facilities, and also use our guidance in order to understand how we are using all the material that you saw before, and also let them work with actual data taken by us and see where they can go with their work. Another thing is that Zooniverse can help us organize this common work in a more democratic way, so that we target exactly what the citizens are curious about, instead of making assumptions about this and trying to answer questions that maybe they don't even have. So now Zooniverse, as I told you, is a platform that is focused on the development of citizen science projects. And it is a gateway for people to participate in the scientific pursuits of various teams around the world. The content of the site helps people get an idea of what we are doing and to navigate different aspects of our domain of study. To say it plainly, to see if they like what we do, if it is their cup of tea. The activities that we are developing would give the visitor a better understanding of the different concepts through practical involvement with the data. And the new information that is going to be extracted from this work, we hope to put it in good use for the betterment of the scientific results in methods as you saw in the previous presentations, and the better understanding of the response of our detectors and the impact on these methods. The discussion, it is of major importance because it will help drive the activities and the content in a more appealing direction for the citizen scientists. We understand that more appealing content will result in more participation, and more participation will give us more analyzed data. And we really want to have this communication and develop new and better materials and new work flows that will better satisfy the interests of the people that want to do muon tomography with us. So I will now go through the site a little bit in order to to let you understand how it works in a few words. So here you see the welcome page, and there is this introductory text that tries to grasp the attention of the visitor. Then you can go to the about section, and from there you dive in the method and many of the things that you saw. So, for instance, we start with the example of the soufriere and how there was this tomography and gravimetry combined results. We go through the analogy with the X-rays because it is intuitively easier to grasp. We see how a shower of particles is developed from the cosmic ray particle, from the primary. The actual principle as it was described with the muons and the opacity and all these steps that we take. We go through the detector and the chain and the detection chain that we have for our experiments. And finally, we have a section where we discuss what consists a signal and what is a background. Because in the activities, we will ask the citizen scientists to identify patterns in our detectors. So it is useful to familiarize themselves with the source of such patterns. Overall, what we wanted is a text that it is easy to read through and that conveys helpful information so that the reader can move forward and start participating actively to dig deeper in the frequently asked questions section and to the educational materials that we are going to develop as this project moves on. The other thing that the next thing that it is very important is the classification, which is the main activity that we have. So the classify button, it takes you to your first workflow. So what you see here, it is on the left a 3D representation of our detector with the 3 planes and the X and Y direction that they monitor. You see these spheres, which is the charge that it is deposited by a particle that crossed the detector. And on the center, you can see these same particles and the charges that they traced on the 3 planes of the detector, but in 1D dimension, so that you can see the exact charge for each point. And here, there is also a simpler reconstruction algorithm that tries to reconstruct what happened. So a particle that passed from up to the bottom in these 2 directions. The participant is asked to say if he thinks that this is a nice reconstruction, if it is what he was going to say himself that happened. And we can see that this is not true. This reconstruction has a false because in the upper part on the left, it goes through a point that has no charge. And he's going to say, no, this is not what I would do. And then he's going to draw what he was about to do. And it is not only this, but there is also the potential to draw orphan points on the detectors, and in this manner give rise to patterns through this data. So the other thing that is very helpful, and this is something that we want to utilize more, is the tutorial part, where if you don't know what is going on or what you have to do, you click there, and then you are brought to a page where you it is explained very thoroughly what you have to do and what steps you have to follow in order to provide a useful result. So right now we have two workflows, the one that I just showed and another one that reaches more complicated topologies. Both of them have the goal to familiarize the participant with the geometry and the response of the detectors. And we also want to open up discussion on the calibration, the detection, and the simulation techniques to better facilitate these workflows. And for us, we expect that in this manner, we are going to be able to revisit our reconstruction and selection algorithms that we use for myography. So in order to close my presentation, our project aspires on gathering people to work on muon tomography and discuss the various aspects that it touches. This is an excellent chance for us to satisfy our citizens' colleagues' curiosity and tell them more about our methods and our procedures. We also would like to try to find a way to make our to make these methods accessible online and maybe if we can with some on-site activities. The final goal, all in all, is to investigate how we can better, how we can make better our techniques and have a better understanding by having people looking at these events and telling us what they think happens there. So you can find, of course, more information about the demonstrators in the Rainforce URL. And the Zooniverse site, what I just presented, should be available during this summer. So this is all that, this is my presentation. Thank you very much.
Thank you very much, Theodoros. This was very nice. So I hope that all participants to the webinar understood that this was a call for good, willing, and citizen scientists, because we believe that myography, maybe as Theodoros showed, maybe a good field and a good domain to play with quite, let's say, simple data, and that there are a lot of developments which may be foreseen from a really basic algorithm of track reconstruction to the more elaborated machine learning techniques. And if there are people of different competence coming from medical imaging domains and so on, they may be interested in participating to those developments. So please, if so, you can join us, of course, and take contact either through the Reinforce interfaces or directly by email or by whatever. So I would like to thank all the panelists for their nice presentation and talks. I would like to also thank the audience because the Q&A session was quite nice, and this showed that the people are interested and asked very coherent and interesting questions. And then I propose that we close the session here, since Francesco told us that we're a little bit out of time by, okay, 10 minutes. That's the stuff, but since he's the master of time, then I will leave him the last word to end this webinar.
Thank you very much, Jacques. You did an amazing job and an amazing webinar. And I want to thank you myself, all the attendees, for being in here today. Jacques wrapped up everything perfectly. You can get in touch. I tried to, well, scatter in the chat as many information as possible for you to benefit of. So just stay in touch, and we will be launching soon another reinforced webinar. And thanks really to all the speakers. So you did an amazing job today, and you kept all the audience really engaged, I think. Thank you really much, and stay in touch with us.
Thanks a lot. Bye-bye. Bye.
Bye. Bye.